In this demonstration, I will present an approach for solving a thermal compensation network design problem using optimization techniques. We will set up and define the problem in MATLAB and use the mixed integer genetic algorithm from the Global Optimization Toolbox to automatically determine the optimal values for our design. I'll show you how to find the component values for our circuit that give a voltage versus temperature curve that is closest to our desired response. The resistance of a thermistor varies with temperature. Our thermistors are specified with a resistance at room temperature and a temperature coefficient. We are given a temperature curve that we would like to see at point B. Our job is to find the best values for the resistors and the thermistors in order to match this curve. In an optimization sense, we would like to minimize the difference between this curve and the curve generated from a particular combination of components. The supplier of our components only has certain sizes available, so this becomes an integer-constrained optimization problem because our resistor and thermistor values must come from the list of available components. I'll now move into MATLAB to show how this problem can be solved. First, I'll create a set of temperature data that ranges from -40°C to 85 in increments of 5. The desired voltage at each temperature is given by the following formula. We plot our voltage versus temperature curve to ensure that it looks right and add the appropriate labels. Now that we have our target, let's load in the list of available components from the supplier. 3 variables were loaded into the MATLAB workspace. Res gives the different resistance values for the 70 different available resistors. The other 2 variables contain the values for the resistance at room temperature and the temperature coefficient for the 9 available thermistors. I have created a function that takes the temperature, component indices, and component values as inputs and returns the voltage versus temperature curve. This function uses the component indices to index into the vectors of component values and then simulates the circuit. This simulation is done inside temp-comp-curve, which, as you can see, evaluates the governing equations for the circuit and then returns the voltage versus temperature curve. To demonstrate how this function works, we will call voltage curve with these indices. What this means is that each of the 4 resistors in the circuit will have the resistance specified by the second value in the res vector, and the coefficients for the 2 thermistors will be the first values from the respective thermistor vectors. If I add the resulting voltage curve to the plot of our ideal curve, you can see that we are very far away from our target curve. For my optimization problem, I would like to find the optimal vector of component indices such that the difference between the simulated curve and the desired curve is minimized. I'm going to use one of the solvers from the Global Optimization Toolbox, the genetic algorithm, which is especially suited for this problem's nonlinear objective and integer constraints. First, I will need to define bounds on each of my variables. My variables will be the indices into the resistor and thermistor vectors, so the lower bounds will all be 1, the lowest possible index for these vectors. The upper bounds will be the length of the vector of available components. I have 70 possible resistors, so each of the first 4 upper bounds will be 70. There are 9 possible thermistors, so the last 2 upper bounds will be 9. All 6 of my variables need to be constrained to be integers. If we look at the documentation for the genetic algorithm, you can see that each value in intcon represents an x component that is integer valued. So I will define intcon as a vector with values 1 to 6. I have created a custom output function in order to illustrate the progress that the optimization solver has made. We can create a function handle to the function to pass it to the optimization algorithm. The last thing we'll do is define the option structure to be used in the optimization. Through this structure, we specify parameters such as tolerances, population size, and generations. A full list of the available options can be found in the documentation for GA-OptimSet. We're now ready to perform the optimization. My objective function that I've specified will perform a simulation of the circuit, and then compute the sum of squares between the simulated results and the desired curve. The number of decision variables for this problem is 6. The bounds, integer constraints, and option structure are also passed to the solver. Now the optimization is running, and the custom plot function is showing the current best simulated curve compared to the desired curve. I'm also using a built-in plotting function to plot the best score and mean score of the solver. The optimization has completed, and you can see the solution here. I'd like to point out that the genetic algorithm is based on stochastic methods, meaning that we are not guaranteed to find the same solution every time. I'll demonstrate this by running the optimization again. You can see the fit getting closer as the genetic algorithm finds better solutions. You can also see that the mean score is decreasing as the algorithm zeroes in on a solution. Optimization has stopped again, and this time returned a slightly different solution.